Hello everyone, welcome to Gate Academy Global. Welcome to Gate Academy. So previously we have discussed everything in detail, that what types of riveting will be there. We have seen the chain riveting, zigzag riveting and the fundamental geometries in that. Now we will be seeing the main procedure of designing, okay, how can we design a riveted connection, and majorly it will be for a lap joint or a butt joint, okay. So before discussing the designing part, it is also necessary that we must understand that what type of failure will be there in the riveted connection, okay. So let us say type of failure, types of failures. So fundamentally we will be having 5 types of failure in a riveted connection, okay. So first of all, let me draw a diagram of a simple lap joint, okay. This is a lap joint. Okay, this is the diameter D, okay. This is the top view of the connection, okay. Let us take 2 rivets, okay. This is the pitch P, okay, and the diameter is D. Now a force P is acting on the connection. Now here, first of all, you can see at the interface of the plate, as I have told you previously, that there will be a tendency to move relative with respect to each other, hence there will be a shearing force, okay, and along this particular plane, there will be a tendency in the rivet to fail under shear. So first type of failure is the shear failure of rivet, okay, shear failure of rivet, okay. Now as you can see that there is a tensile force acting on the plate, okay, and here due to the presence of rivet hole there is a discontinuity in the plate, okay, and if the thickness of the plate is T, let us say if the thickness of the plate is T, then at this location, that is near discontinuity, the area of material in the plate is minimum, okay, the material is minimum near this discontinuity, okay, and here you can see that width of the plate is not given, okay, hence we will be considering the per pitch length for our calculations, okay, for our calculation we will be considering the pitch length of the rivet. So in the pitch length, if there will be no hole, then the width of the plate will be equal to the pitch, and as here you can see that there are 2 holes, hence this distance will be equal to P minus D, okay. So between 2 consecutive holes, that is for a pitch length, the width of the plate material is P minus D, okay, where D is the whole diameter, or you can say the diameter of rivet, as the connection has been formed, and after forming the connection the rivet will be filling the hole completely, hence the rivet and the hole will be having the same diameter, okay. So P minus D is the width of the plate in a pitch length, okay. Now due to this reduction in the width of the plate, the stress will be high at this location in the plate, okay. So there will be a tendency in the plate to tear apart along this plane. So second type of failure will be due to excessive tension, and due to this excessive tension the plate will tear about this plane, okay. So the second failure which we can observe is the tearing of plate, and this tearing will happen between 2 consecutive rivets, okay, tearing of plate between 2 consecutive rivets, okay, between 2 consecutive rivets. Now as you can see that there is load acting on the plate, and due to this load, as the rivet is fixed in the hole and this plate is trying to move in this direction and this plate is trying to move in that direction, then what will happen, this force will try to pull the rivet along the direction of the force, and this force will try to pull this portion of the rivet along the direction of force. Now this motion along the direction of force will be restricted by the plate, okay, by the plate. So at the contact surface between the rivet and the plate, at the contact surface between the rivet and the plate, which will be a cylindrical shape, a pressure will be developed, okay, and that pressure will cause a stress that will be compressive in nature over the surface of plate as well as on the surface of rivet, and that is called crushing stress or the bearing stress, okay. So due to this bearing stress, what will happen? The diameter of hole may increase or the diameter of rivet will decrease, because if this is the hole, the bearing stress will be acting on the hole like this. So this will try to increase the diameter of hole, okay, and this same force will be acting on the rivet, and due to this the diameter of rivet may reduce. So the rivet will deform under this compressive stress as well as the hole will also deform under this compressive stress, and this compressive stress is known as bearing stress, and as this is compressive in nature, okay, and this will deform, that means this will contract the rivet or it will enlarge the hole, hence it is also known as crushing stress, okay, bearing stress or crushing stress. So bearing or crushing stress will be there. So due to this bearing or crushing stress, crushing failure of rivet will take place, okay, So third is the crushing failure of the rivet, okay, crushing failure of the rivet. Here while designing, the enlargement in the size of hole will not be considered, okay, we will be considering the deformation of the rivet, because the hole must not deform. This is the criteria. So before the deformation of the hole, there should be deformation of the rivet. So definitely the rivet material will be slightly weaker than the plate material in compression, clear, so that the shape of hole will not change, because if the shape of hole has been changed, then we will not be able to make a riveted connection again. If the rivet is failed at that particular hole, then we will be able to remove the rivet and we will be putting a new rivet at that location, and the joint will be working as it was working before. But if the hole has been deformed, then the entire plates has to be replaced, and this is not desirable, okay. So design is to be done in such a way that before the change in shape of the hole, there should be a deformation in the rivet, so that we will be able to judge that deformation has occurred and we will be replacing the rivets. But in numerical problem, you will see that only one crushing strength is given, okay. As I have told you that the crushing strength of the rivet and the plate must be different, okay. So the crushing strength of the rivet material should be slightly lower than the plate material, but in GATE examination or in different examination, you will see that there is only one strength, or it may be the compressive strength of the material, that will be the crushing strength, because crushing is nothing but a compressive stress, okay. So the compressive strength of the material will be given in the problem, and you will see that only one value will be given, okay, that will be for plate or that will for the rivet or for the both, okay. So in majority of cases we will have the same value of crushing strength for the rivet material and for the plate material. So in such a problem, if there is only one crushing strength given in the question, okay, then we will be considering the crushing of plate also. So we will not consider only the crushing of rivet, but also we will consider the crushing of plate, okay. Crushing of plate will also be considered, okay. So how can we judge these conditions? If sigma c is, say, sigma c permissible, you can say the permissible compressive stress is same for rivet and plate, okay, rivet and plate. Now if I say that sigma c for rivet is less than sigma c for the plate, that means the plate is stronger than the rivet, in that case design will be based on the crushing strength of the rivet, because definitely under the action of load the rivet will fail first, okay. So design will be based on crushing strength of rivet. Okay, so the crushing strength of rivet will decide the permissible load in crushing. Okay, now the next type of failure, that is the fourth mode, is the shearing of plate. Okay, is the shearing of plate near the edge, Now as you can see, if this is a rivet, okay, so this is the edge of the plate. Now here we are applying some force, okay, so this is subjected to a force like this. Now at the bearing area you will see a bearing stress, that is the compressive stress, or you can say the crushing stress, but also due to this crushing, this rivet is trying to push the material of the plate in this direction. Okay, now here in this area you can see that there is no force. Okay, so the material in a certain region over here will try to move under the action of this load in this direction. Okay, and hence somewhere here you can see there will be a tendency of a slip, that means relative motion. So the material will flow in this direction, okay, under the action of the external force, and a shear will take place along these planes. Okay, so this will be near the edge of the plate. Okay, and if the rivets are placed very close to the edge, this tendency will be very high. Then how can we observe it? How can we picturize this condition? Suppose you have just took two papers, okay, and join them with a stapler pin. If the stapler is very close to the edge, it will be very easy for you to just break the joint. And as soon as you break the joint, just observe the region where the failure has taken place. You will see that some material, that is some paper, have teared down from the edge. Okay, so that is due to the shearing. Okay, so here the material will move in this direction due to this particular force, and this is known as the shearing of plate near the edge. Okay, for that sufficient distance should be there, because as we have very small material over here, we have very less quantity of material over here, so less resistance will be there. Okay, because this area, the area in this particular length, okay, will be the area which will be resisting the action of external force. So if the area will be the less, the shear stress in this region near the edge will be high, as stress is inversely proportional to area. Area is low, stress will be high. So if the rivets are placed very close to the edge, the area which will be resisting this shear will be low. Okay, hence the stress will be high, and there will be greater chances of shearing of plate near the edge. Okay, now the fifth one is crushing. Okay, is crushing of plate near the edge. So as I have told you, this force is trying to move this material in this direction. Now if there is no shear action only, okay, if there is no shear action, but there will be a deformation, as there is very less material, in this region. So if there is not a sufficient gap between the edge of the plate and the rivet hole, then there will be a tendency to crush under the action of the load. So the diameter of hole will change due to crushing near the edge of the plate. Okay, and that is known as crushing of the plate near the edge, and for that a sufficient distance is to be considered, that is known as margin. So shearing of the plate or crushing of the plate near the edge can be easily avoided by taking a certain distance, that is known as margin. Okay, now we will see how we can design this type of joint. Okay, so here I have taken the lap connection or the lap joint as a example. Now the procedure will be the same for a lap connection or for a butt connection. Okay, so let us just start. So design of lap joint and butt joint. Okay, so write down the heading. So in design of lap joint or butt joint, basically we will see three types of stresses. Okay, as you analyze the different types of failure, you will see there are basically three types of failure. That means the tearing failure, the shearing failure and the crushing failure. So basically there will be three types of stresses: tearing stress, shearing stress and crushing stress. So basically we will be dealing with only these three types of stresses. If you won't consider the location at which the failure is occurring, then we have only three types of stresses, or you can say three types of strength, or you can say three types of mode of failure. Okay. Now if you have a rivet only, okay, and you have a plate, now in this situation I am not talking about a riveted connection, I am just dealing with a rivet or a plate. Okay. So if you have a rivet, after discussing this we will be able to understand the connection in a broad manner. Okay. This is very conceptual. So in riveting we will have a rivet and a plate with hole, with a plate with hole. Okay. So let us talk about the rivet first. So for rivet, okay, rivet will look like this. This is the head of the rivet, this is the shank portion, okay, this is the tail. Okay. Now this is the diameter of the rivet, D. D is the dia of rivet, Now it is not possible for you to tear the rivet. Okay. In any situation, even if there is a joint, you cannot tear the rivet. There is only two types of stresses which can be induced in the rivet. So under the action of load, your rivet may shear along a plane like this. If this is a rivet connection, then your rivet may fail along a shear plane like this, or under action of load it will be subjected to a compressive force and hence it will fail due to crushing. So only two types of failure can take place in a rivet, that is a shear failure and a crushing failure. There is no possibility of tearing failure of the rivet. Okay. So basically in order to withstand these two failure, this must have two strength, that is shear strength and the crushing strength. Okay. So the rivet can fail due to shear and crushing. Okay. So the shear strength of the rivet and crushing strength of rivet will be defined. Okay. Now let us say that it is the area which is under crushing and it is having a height T. Okay. So you can write the crushing stress, okay, sigma C for rivet is equal to PC, crushing load for rivet, divided by area under crushing, that is the projected area. Okay, that is the projected area, and the projected area will be equal to T multiplied by D. Now why we are taking the projected area? Because during the crushing the compressive force will be acting on the surface of rivet, and the surface of rivet is having a curvature. It is not a flat surface. Okay. So hence we will be taking the projected area of the rivet in order to have the value of the crushing stress. Okay. So the projected area will be D into T. Now it may have a shear stress, okay, tau of rivet, and this will be equal to PS, the shear force on rivet, divided by the area under shear, that is pi by 4 D square, okay, where D is the diameter of the rivet. Okay. So based on this, if the strength of your rivet material is tau permissible for rivet, okay, this is the permissible stress, tensile stress, this is permissible tensile stress for rivet material, okay, and if tau permissible is the permissible is the permissible shear stress for rivet material, then based on these values, what should be the case? The stress induced in the rivet, in a single rivet or n number of rivet, must not exceed the permissible stresses. Okay, so for that particular situation, the load acting on the rivet must not cross a certain value, so that the stresses induced will be less than or equal to the permissible stresses. So based on this idea, we can calculate the permissible load on the rivet. Okay, so the permissible load for the rivet, permissible load for rivet, So first of all, in crushing, PC for rivet, okay, will be equal to D into T into sigma C permissible. Okay, sigma C permissible. This is the permissible crushing stress. This is permissible compressive or crushing stress. Okay, so this load should be there. If you apply a load more than this, then there will be a crushing failure, and if you want to make a safe rivet, then in that case the load should be less than PC. Okay, now for shear failure or for shearing, PS of the rivet should be equal to pi by 4, okay, D square into tau permissible, and this is the permissible shear stress in rivet. Okay, now if I talk about the strength of the rivet, that which one is the strength of the rivet? As I have told you, in subject of machine design, we will be discussing the strength as the load carrying capacity, the maximum load which can be applied, because this will be very easy to understand. As here in a design problem, you may have two different rivets. Okay, they may be made up of same material, but they have different dimensions. So in terms of maximum stress which they can vary, they can be subject, they will be fail at same value of stress. But before failing, the rivet which is having a larger size will carry more load. Okay, so it is a basic idea that a common person will not understand your term stress. He will not get idea that at which point the stress will exceed the permissible value. So we must tell him that this much load should not be applied. Okay, you should apply a load minimum than this value for a safe design or for your safety. Okay, so we will consider the load, the maximum load which can be applied safely, as the strength. Okay, so the strength of rivet, if you talk about the strength of rivet, so the strength of rivet will be minimum of PS rivet and PC rivet. Okay, so the least value between these two values will be the strength of the rivet, and this strength is defined as the load carrying capacity. Okay, and if there are n number of rivets, so multiply it by n. If there are n number of rivets, multiply the equation by n, and then the same method will be followed to consider the strength of the rivet. Now, as here we are not discussing about the riveted connection, we are discussing only about a rivet. Okay, so the part of rivet is completed. Now, if you have a plate, so let us talk about plate. So for plate we have only one condition, that if you have a simple plate without any hole and you are applying load on the plate, okay, let us say width of the plate is W, thickness of the plate is T, then due to this load P, you can see that a tensile stress sigma T will induce, and this will be P divided by W into T. Okay, now what will happen, as to facilitate a rivet in the plate, we must create a hole. Okay, and just because of the hole, the material will reduce, that means the critical area will reduce. Here the area is W into T, but due to presence of a hole, the area of cross section at the plane where the stress is maximum will reduce. Here the cross section area is uniform throughout. Okay, so stress will increase, basically the stress will increase due to presence of hole. Okay, so now let us draw holes. So I want to facilitate two rivets. Okay, or you can say n number of rivets are there, n number of rivets are there, so n will be number of hole also. Okay, now here I have considered the dimension of the plate, but if you don't have the dimension of connection, then in that case we will consider the pitch length of the rivet, and the calculations will be based on the per pitch length. Okay, so the number of elements present in a pitch length will be considered for designing, and this was also the part of our previous lecture. I have told you there that if you don't have the size of plate or the riveted connection, then we will consider per pitch length for our calculation. Okay, so here this is the pitch of the rivet. Okay, now in this pitch length, this is P minus D. This is P minus D, where D is the P minus DH. DH the diameter of hole. So we have two holes, and DH is the diameter of hole. Okay, diameter of hole. Now the thing is, we have not formed the joint yet. There is no riveted joint. We are discussing about a rivet and a plate separately. So here in this case, DH is not equal to D. DH is not equal to D. And this is very important point, because there is no joint. There is no joint yet. Okay. Now due to formation of this hole, the value of stress induced in the plate will increase. Okay. Now if there is no hole, then for the same pitch length, if there is no hole, then for a pitch length sigma T will be equal to P divided by P into T, small p, that is pitch into T. And as we are having a hole, okay, we are having a hole in the plate, so due to presence of the hole, okay, due to presence of hole, sigma T in the plate will be equal to P divided by small p minus DH into T. Okay, so this will be the stress induced in the plate due to presence of holes. Okay, due to presence of holes. And if there are n number of plates, if n is equal to number of holes, then you can write P sigma T for plate is equal to P divided by P minus n into DH. As there are n holes, so DH will be multiplied by the number of holes into thickness of the plate. Okay, and if sigma T permissible is the permissible stress in the plate material, as I have told you earlier that the strength may be different for the rivet material and the plate material, and it may be same for both. Okay, so if sigma T permissible is permissible tensile stress for plate, then this sigma T plate, that is the induced tensile stress in the plate, must be less than or equal to the sigma T permissible. This should be the condition for safety. Okay. Now for limiting condition, for designing we will use the limiting condition so that we can find out the maximum load which can be carried. Okay, so for designing we will take limiting case. So for limiting case, sigma T of the plate will be equal to sigma T permissible, Okay, Hence, we can write P, okay, P, let us take it PT. So, the PT is, represents a tensile load, okay, so it will be more convenient representation wise. So, this will be PT, let us take us as PT, okay. So, this will be more convenient for our representation, okay. So, PT is the tensile force, okay. So, PT divided by P minus D, P minus N into dH into T will be equal to sigma T permissible, and on solving this equation we can have our results. If the diameter of hole is known, then we can find out the load, okay, and if the load acting on the plate is known, then we can find out the diameter, okay. So, if you want to find out the maximum load that is maximum tensile load which the plate can carry, so this will be your tensile strength, or you can say tearing strength, because due to this tensile force the tearing of plate will occur between the two consecutive rivets, okay. As I have told you in the mode of failure that due to presence of the rivet hole in the plate, there will be failure of the plate between the two consecutive rivets, okay. So, tearing failure, to avoid tearing failure, avoid tearing of plate between two consecutive rivet hole, okay. PT should be equal to or less than this value, that is P minus N into dH, okay, into T into sigma T permissible, and here we have taken sigma T of plate and the permissible stress equal, so we would be needing the inequality. So, this should be the maximum value of load which it can take to avoid the failure of the plate between two consecutive rivets. So, this is the maximum load, that is the maximum, this is the maximum tensile load, So, in the case of a plate which is having a hole, you can see there is only one strength which is related to the plate, that is the tearing strength, okay. So, the plate should not tear during the loading, okay. Now, after discussing the various strength of a rivet and the plate, now we will be going to form a joint. So, after forming the joint, we will have three strength, because for plate, that is strength of plate is nothing but PT, okay, as there is no other stress in the plate, because plate is carrying only hole. Now, after the joint is made, there will be shearing of the plate and the tearing of the plate also, okay, as we have seen earlier. But if there is no joint, then in that case the only stress due to which the plate can fail is the tensile stress, or you can say the tearing stress, okay. So, after joining the plates, what will happen, as we have considered initially, that in the riveted connection the rivet will completely fill the hole, okay. So, now we will talk about riveted joint, that may be a lap joint or butt joint, okay. The diameter of the hole and the rivet will be the same, okay, dH and D, okay, will be same, or you can write D equal to dH, okay. This is the first important point, okay. So, first type of failure will be the shearing of the rivet. Second type of the failure is shearing of the crushing of the rivet and the plate, and third is the tearing of the plate between two consecutive rivets, okay. So, if I talk about the strength of joint, okay, so we will be having three values, that is PS, PT and PC. PS, PT and PC. We will be having three values, okay, and the strength will be the minimum of these three values. So whichever is the minimum value, that will be the load carrying capacity of the joint. Now how is it possible that we will be taking the minimum value as the strength? Now if let us say PS is 100, PT is 150 and PC is 80. That means this is PS, this is PT, this is PC. So this means that the joint, that is riveted joint, can take 80 units of load to avoid the crushing failure. Now if you choose the greatest value, that is 150 units as the allowable load, then this may not fail due to tearing, but as it is very clear from the values that it can take only 100 units of load for shearing, to avoid shearing, and it can take up to 80 units of the load to avoid crushing. And if you apply a load of 150 unit, then it will definitely fail due to crushing as well as the shearing. Hence, in order to make a safe joint, we must take the least value of the load. Okay, so here we will be choosing the minimum of PS, PT and PC, and this will be the strength of joint. Okay, and for the calculation here, use DH is equal to DS. Okay, now let us start with the lap joint. Okay, let us start with the lap joint. So in lap joint we will have a rivet. Okay. Okay. Now PS, that is the shear strength of rivet. Shear strength of rivet. Now I am writing everything in short because the concepts are clear from the discussion based on rivet and the plate. Okay. So PS, that is the shear strength of rivet in joint will be equal to the area under shear, that is pi by 4 d square. Again remember, both are equal, so pi by 4 d square into tau permissible. Now if there are n number of rivets, so multiply this equation by n, which is the number of rivets. Okay, number of rivets. Also you can call it n is equal to number of rivets per pitch. Okay, so number of rivet per pitch will be used, or you can also write it as a small n. If you want to write it as small n, you can write small n over here. So small n will be the number of rivet per pitch, and this will be used if the dimensions are unknown. Okay, that is if size of connection, or you can say or plate is unknown. Okay, is unknown, then we will go for the number of rivet per pitch. Okay, and this has been discussed in previous lecture. Okay, then how can we calculate the number of rivet per pitch? So if it is a single riveted lap joint, so n will be equal to 1. Okay, n will be equal to 1 for single riveted joint. Okay, n will be equal to 2 for double riveted joint. Okay, n will be equal to 3 for triple riveted joint. For quadral it will be equal to 4. Okay, so it will go on based on the number of rivets per pitch. Okay, it will move on like this up to n. Now in case of the butt joint, there will be a situation where double shear will take place. I will be telling you about that. Okay, so this is the shear strength of the rivet joint, or you can say a lap joint. The similar formula will be used for butt joint, but in butt joint there is a possibility of having a double shear, so I will write the formula for that separately. Okay, now there will be a crushing failure PC, that is the crushing failure. To avoid crushing failure, the crushing strength, okay, crushing strength of riveted joint, if T is the thickness of the plate, then you can write PC as D into T into sigma C permissible. Okay, and if n is the number of rivets per pitch, then multiply it by n. So this will be the crushing strength of the riveted joint. Okay, crushing strength of the riveted joint. Now one more important point about this, that if there are two dissimilar plates. That means the thickness of the plates are different. This is T1, okay, and this is T2. This is T1 and this is T2. Okay, so in that case, if you want to design the riveted joint for crushing, then the crushing strength will be calculated based on the minimum area. Why is it so? Because if area is minimum, stress will be high and there will be greater chances of failure from that location. Okay, so the bearing stress will be more critical for the plate having a lower thickness. So here, as from the diagram you can see that T1 is less than T2. Hence, the crushing failure will be a severe problem in the thinner plate as compared to the thicker plate. Okay, so if two dissimilar plates are there, then use thinner plate for calculation of crushing. Okay, so if T1 is less than T2, then PC will be equal to T1 into D into N into sigma C permissible. Okay, or if T2 is less than T1, then PC will be equal to T2 into D into N into sigma C permissible. Okay, clear? Now in both the situation, like in case of the shear of the rivet joint or crushing of the rivet joint, if the total number of rivet is known, that means the dimensions of the connection is known. If dimension of connection is known, okay, so in that case N will be equal to, capital N will be equal to total number of rivet, okay, total number of rivet, okay. And if you assume, as in assumption part I have told you that we will assume that in a lap connection or a butt connection, we will assume that the line of action of the external load is passing through the centroid of the arrangement. So yeah, due to that assumption, the load will be distributed equally among the number of rivets. Okay, so if N is the total number of rivet, then in that case you will write PS is equal to N into pi by 4 D square into tau permissible, okay, and PC as N into T, or you can write T minimum, that is the minimum thickness of the plate if you have two dissimilar plate, okay. And if if the two plates are having same thickness, then T minimum will be same for both the plates, okay. So T minimum you can write into D into sigma C permissible, okay, into sigma C permissible, okay. Now let us talk about the tearing strength, okay, tearing strength, okay, tearing strength. So tearing strength for riveted joint, not for the plate only, it is for the joint. So riveted joint, okay. So again here also DH will be equal to D, both will be having same size because the rivet has completely filled the hole, okay. Hence if the size of the joint is not known, like this, size is not known, but we can see that there are two rivets in a pitch length, okay. Or you can see that there are only one rivet in the pitch length, okay. So here in this condition we have two rivets in a pitch length, so it is a double riveted connection, okay. So the tearing of plate will occur between two consecutive rivets. So in this plane the tearing of plate will happen, the tearing of the plate will happen in this plane, okay. And here if D is the diameter, then P minus D is the width and the thickness of plate is T, okay. So the tearing strength PT will be equal to N, okay, it will be equal to it will be equal to P minus D into T into sigma T permissible. Okay. Now here the tearing strength is not affected by the number of rivets per pitch, because if we have two rows, that means there is two rivets per pitch. So here you can see the width is P minus T, and here also the width is P minus T. So basically both the rows are giving us a same value of critical area. So the area which is carrying the maximum stress is same for both the rows. Hence here we don't have to consider the number of rows. So this will not be multiplied. Okay, this will not be multiplied by the number of rivets per pitch. But if the size of plate is known, okay, it is important, okay, if size of plate is known, let us say the plate is having a width equal to W, and here we have 3 rivets like this, okay, 3 rivets. Now here we have a tensile force, okay, tensile force equal to P, okay, the thickness of the plate is T. Now here when the size of the plate is known, or you can say the size of arrangement is known, okay, is known. So in that case we will consider the number of rivet present in the bolt, okay. So here we have only one row of the rivet, so this single row will be having the most critical area. So here we will not consider the pitch, the width of the plate per pitch length, as here this P minus D is the width of the plate per pitch length. Okay, this is the width of the plate per pitch length, as the dimensions are unknown. So if the dimensions of the joint is unknown, or you can say the width of the plates are unknown, then in that case we will be designing the riveted connection based on the per pitch length. But here the dimension is known, so we will be considering the entire dimension, and here in this example we have a single row of rivet. So if I ask you that what is the width of material at this area, so this is minimum area, this is A minimum for the plate, and hence the stress will be high in this location, so this will give me sigma max. So here the stresses are maximum. Now in this riveted joint we will be avoiding the effect of stress concentration as we have assumed previously in the assumption part, because this will be made up of a ductile material, and also the loads are basically static in nature, there is very less fluctuation in the load, hence the effect of stress concentration can be neglected, okay. So sigma max will be at the A minimum. Now what will be the A minimum? As you can see, this is our rectangular cross section. So here in this section the width can be written as W minus number of rivets into D, okay, this will be the width, and the area will be multiplied by T. So this will be the minimum area, okay. So sigma max, that is the tensile stress sigma T, this will be equal to P, or you can write it as PT, the tensile load PT divided by W minus N into D into T, okay. W is the width of the plate, okay. Now to avoid failure, this should be less than equal to sigma T permissible, okay. So the permissible load to avoid tearing, okay, will be PT equal to we will equate these two values, we will use the limiting case, okay. So we will be getting the same result like this, but here the term will be like this, this will be W minus N into D into T into sigma permissible. So the concept is same, but the difference is that here we have considered the total number of rivet present in the connection, hence we will be having a minimum area, and there will be the effect of total number of rivet present in the connection. So total number of rivet present in the connection is N, capital N, okay. So this will be the minimum area, so minimum area multiplied by the permissible stress will be giving me the permissible tensile load. So this is the permissible tensile load for such case, okay, permissible tensile load, okay. So if there is a dimension of the plate, then the things will be different, okay, for the tearing load. Now, so we have understood the shearing of the connection, okay, crushing of the connection and tearing of the connection in case of a lap joint. Now let us see about what will be the difference if there is a butt joint, okay. So if there is a butt joint, there will be some difference as compared to the lap joint, okay, and we know that to form a butt joint we will use a cover plate, okay. So this is a butt joint, this is a butt joint, okay. So first of all we will discuss about the single cover butt joint, single cover butt joint, okay. Now the thing is to join two plates in end-to-end connection, that is to get a butt joint, this will be the placement of the plate, and here we will use a cover plate. This is your cover plate, this is your cover plate, okay. Now as this is the cover plate, okay, so the cover plate is in an overlapping contact with the plate number 1 and plate number 2. So here we will insert the rivet like this, okay. Now if you draw the free body diagram of each portion, then you will see that there is lap connection between this cover plate and the plate number 1. So here in butt joint we won't consider the both side of the cover plate, we will consider only one side of the cover, either this side or this side, not the both side, okay. So if I ask you that what is the number of rivets per pitch, so here as you can see there are 2 rows of rivet, okay, that this is the first row, this is the second row. So it doesn't mean that it is a double riveted joint. No, in butt joint it is very essential to have 2 rows of rivet. One is on the side of first plate and second row will be on the side of second plate, okay. So here to consider the number of rivet per pitch, that is the number of rows in the riveted connection, we will be seeing only one side of the connection, that may be on the part of first plate or that may be in the part of second plate. We will not see the entire connection at a same time. So if you see the entire connection at the same time, you will find there are 2 rows, okay, in left and right side. So you will get confused that there are 2 rows in the riveted connection, but there is only 1 row, okay. So this is the fundamental thing which you must understand, okay. Now we will be analyzing this only. So here you can say this is a single riveted butt joint, this is a single riveted, this is a single riveted butt joint, okay. So I hope that you will be able to observe that which kind of butt joint is given in the question, okay. So this means the single riveted butt joint. If you add another row in this side and this side, then there will be 2 rows in one side of the junction, hence this will be known as double riveted. If you add 3 rows in the side of first plate, then it will be triple riveted. If you add 4 rows, it will be quadruple riveted, clear. Now here you can see that it is having only one interface. Here for single cover butt joint we have only one interface, hence the number of shear plane is only 1, okay. So here also in case of single cover butt joint PS will also be n into pi by 4 d square into tau permissible, okay. So this will be same as lap joint, same as lap joint, because it is giving the similar behavior, that is single shear is there in this single cover butt joint similar to the lap joint, okay. So it is giving a single shear, okay, single shear is there, single shear is there in the single cover butt joint. Now if you use double cover butt joint, okay, so for double cover butt joint, this will be the situation. This is plate number 1, this is plate number 2, okay, this is the cover plate, okay, this is the cover plate and this is the rivet. Now this is again a single riveted joint, okay. So I hope that you have got the idea to observe that what kind of riveted connection is given in the problem. Okay, now here if there is a force acting on the connection like this, then you can clearly see that definitely this rivet may shear along this plane and this plane. So if I ask you how many planes are there, that is how many shear planes are there, so there are two planes along which the rivet can shear. Okay, so this may shear like this. This is the first portion, this is the middle portion, this is the lower portion. Okay, so this is the first shear plane, this is the second shear plane. So this is known as double shear. This is known as double shear. So in case of double shear, the area under shear, that is pi by 4 d square, will be multiplied through the will be multiplied by 2, as there is double shear. Okay, so in this case you will write Ps is equal to n into 2 into pi by 4 into d square into tau permissible. Okay, okay, or you can write it like this: if z is the number of shear plane, okay, if z is equal to number of shear plane, then Ps will be equal to n into z into pi by 4 d square into tau permissible. So this is the formula which can be used in any situation. Okay, for lap joint, if I ask you for lap joint, z will be equal to 1, and for single cover butt joint, again the z will be equal to 1, okay. For double cover butt joint, z will be equal to 2, okay, and n is the number of rivet per pitch, okay, and this has been discussed earlier. So for any problem, if you understand what is the value of n for certain condition and what will be the value of z for certain condition, then this formula can be used for any type of joint. That may be a lap joint, that may be a single cover butt joint, that may be a double cover butt joint. Okay. Now for crushing also, as you can see, there is very huge similarity between the butt joint and the lap joint for designing. As far as designing is concerned, there is very large similarity between the lap joint and the butt joint. Okay. Now if we talk about the crushing failure, then also we have to consider few things, that if the thickness of cover plate is different from the plate to be joined, okay, so butt joint in crushing, okay. So if the thickness of cover plate is different from that of the plate, if thickness of cover plate is different from the plates, so let us say Tc is the thickness of cover plate, okay, so it is less than thickness of the plate T. Now here you can see that if this is the rivet, this is the cover plate, this is the thickness of the cover plate, that is Tc, okay, this is the plate, okay, this is the plate, okay. So this condition is similar to the condition which we have discussed earlier, that is the lap connection of two dissimilar plates. So for the crushing failure, we will take the minimum thickness, okay, to calculate the area under crushing. So here the crushing will be severe at this location, okay. So we will take the area of crushing equal to Tc into D. Okay, as you can see that Tc is less than T. Okay, so this concept is same as that concept, there is no difference in concept. Okay, but if the thickness of cover plate is not given, if thickness of cover plate is not given, so in that case you will assume that the cover plate has same thickness as that of the plane. Okay, so if Tc is not given, assume Tc is equal to T, that is thickness of cover plate is equal to the thickness of the plate. Okay, so this will be the area under crushing, and then the formula will remain same. Okay, this will be N, that is the number of rivet per pitch multiplied by the thickness of the plate into D into sigma C permissible. Okay, sigma C permissible. And the formula for tearing of the plate will be same. There will be no difference for the tearing of the plate. Tearing will be occur at the distance between two consecutive rivets. Okay, that is P minus D. Okay, this at that particular width the tearing will occur, and we know the concept of tearing of the plate. Okay, so here also the strength of the connection, strength of butt connection will be the least value of PT, PC and PS. Okay, so the PT, that is tearing strength, okay, tearing strength PT same as lap joint, okay, same as lap joint, same as the lap joint. Okay, so this will be PT equal to P minus D into T into sigma T permissible. Okay, this will be same as that of the lap joint. Now the strength of butt joint, the strength of butt joint is equal to minimum of PT, PS and PC. So this will be the strength of the butt joint. Okay, now you may have a lap joint or you may have a butt joint. There is a term that is known as the efficiency of the joint. So let us talk about the efficiency of the joint. Okay, so make a heading, a new heading, that is efficiency of joint. Efficiency of joint. Okay, or you can say riveted joint. Efficiency of riveted joint. Now what does it mean by efficiency of riveted joint? So if there is no rivet in the plate, so the plate will be able to carry a certain load. Okay, now as a riveted connection is there, okay, as a riveted connection is there, so it may be able to carry a load less than that. Okay, so it will carry a load less than that. So previously if there is no rivet, so in that situation, if P, T was the tensile load acting on the plate, okay, so it was able to carry this load. Okay, so let us say PT dash or PT is the strength of plate without hole. Okay, so how can we calculate? It is very easy, as I have told you earlier, that if this is the strength of plate, sigma T permissible is the strength of plate, then PT will be equal to W, okay, into T into sigma permissible, which is where W is the width of the plate, and if W is unknown, use per pitch length, that is P. Okay, that is P, pitch. Okay, so here we will use a per pitch length. Okay, this is the location where possibly we will put the rivet. Okay, so for per pitch length, this PT of the plate will be equal to PT into T. Okay, P into T into sigma permissible. Okay, this will be the strength of the plate. Okay, PT is the strength of the plate without hole. Okay. Now, as we have formed a riveted joint, we have removed certain material from the plate and there is a reduction in the area. Okay, hence now after forming the joint, that is after joining two different plates, the load carrying capacity will reduce. Okay, so now it is carrying a load less than the previous value. Okay, and what load the plate can carry will be the strength of plate, that is the least among PS, PT and PC. So the load which it can carry after riveting divided by the load which the plate can carry before riveting will be the efficiency of the joint. Okay, so efficiency of joint is equal to the strength of riveted joint divided by strength of plate. So this is the efficiency. Okay, so here the idea is, if there will be no rivet, there will be no reduction in the load carrying capacity of the plate, but due to some necessities we have to join two different plates, we have to form a riveted connection. Okay, hence the efficiency will reduce. Okay, that means the load carrying capacity will reduce, and the reduction in load carrying capacity which the joint can give will be the efficiency of the joint. And if there is no change in load carrying capacity even after forming the joint, then the efficiency will be maximum. Okay, if the load carrying capacity is very less after forming the joint, then the efficiency will be tending towards 0. So efficiency is basically comparing the load carrying capacity of the plate when there is no hole to the condition when there is rivet holes. That means when the riveted connection is been made, in that situation what load the plate can carry divided by the load which it can carry without rivet will be giving you the efficiency of the joint. Okay, so the strength of the rivet is the minimum of PT, PS and PC of joint. Okay, of joint divided by the strength of the plate. Now strength of the plate is this. Okay, that is P into T into sigma permissible, or you can write sigma T permissible tensile stress. Okay, sigma T permissible. In many cases, and I can say that in most of the case in GATE examination, you will see that the tensile strength for the rivet material and the plate material will be the same. Okay, so this is the efficiency of joint. Okay, this is the efficiency of joint. Now there is another efficiency that is known as the tearing efficiency of the joint. Okay, let us see that what is tearing efficiency. So tearing efficiency. So tearing efficiency is the ratio of the tensile load which a riveted joint can carry to the tensile load which a plate can carry. So if you have a riveted plate like this, if you have a plate, let us say it is having two rivets and another identical plate is there where there is no rivet hole. Okay, so in this case anyone can tell me that the load carrying capacity of a riveted plate will be less as compared to this plate, a solid plate. Okay, so here the efficiency of tearing, that is tearing efficiency, is comparing the reduction in the load carrying capacity under tension when a riveted hole is present in the plate. Okay, so if there is a rivet hole, now here I am considering that the width of the plate is not given. So if the width of plate is not given, then I will be considering the per pitch length. Okay, this is the pitch, so I will be considering only the per pitch length. Okay, so for per pitch length, in first case PT will be equal to, here this is, say, let us say this is first case, this is second case. So PT, that is for solid plate, that means you can say without hole. Okay, without hole, this will be having a load carrying capacity of P into T into sigma T permissible. Now there are rivet holes, so PT dash, that is for plate with hole, for plate with hole, or plate with hole, okay. This will be area under tension. Area under tension will be, again you know that this will be P minus D or DH you can say, okay, P minus D or DH, okay. So P minus D into thickness of the plate, that is T, into sigma T permissible, okay. And it is very obvious because this value is less than this value. If this is area 1 and this is area 2 between pitch length, okay, between a pitch length, if the area of material is A1 in the first case and area A2 is in second case, then definitely A2 is less than A1, okay. This is A2 and this is A1, okay. Hence PT dash is less than PT, okay. Now we can write down the formula for the tearing efficiency. So the tearing efficiency will be the ratio of eta tear is equal to the ratio of tearing load carrying capacity, or you can say tearing strength of the plate, tearing strength of a riveted plate divided by tearing strength of a plate without hole, okay, without hole. So you can solve this. So this will be equal to P minus D into T into sigma T permissible divided by P into T into sigma T permissible, okay. So this tearing efficiency will be, this will get cancelled, okay. So this will be 1 minus D divided by P, okay. Now multiplied by 100%, then you will be getting the tearing efficiency. So eta tear, okay, eta tear will be equal to 1 minus D divided by P into 100%, okay, where D is the diameter of rivet hole, okay, D is the diameter of rivet hole or rivet, okay. D is equal to dia of hole, okay, D equal to the dia of hole or rivet, okay. Whatever is given in the question, you will be assuming that value. If it is there, that like in a riveted connection, the diameter of rivet is like D is the diameter of rivet and P is the pitch length of the rivet, then what will be the tearing efficiency? So for that particular question, you will be solving for tearing efficiency using the value of diameter of rivet and the pitch length, okay. So D is the diameter of hole or rivet and P is equal to the pitch length, okay, pitch length. And if the width of the plate is given, okay, this formula is useful when width of the plate is not given, when width of plate is not given, okay. Now but if the width of the plate is given, okay, if width of the plate is given, if width of plate is given, okay, so in that case PT without hole, okay, without hole will be equal to W into T into sigma T permissible, where this is the area, W into T is the area, okay, and PT dash is with hole, this is the tearing strength, okay. So PT is the tearing strength without hole, sorry, and PT dash is tearing strength with hole. So with hole, this will be W minus N into D, okay, or you can write DH, okay, multiplied by T into sigma T permissible. Okay, so dividing both these values, you will be having the value of tearing efficiency. Okay, so tearing efficiency for such case, tearing efficiency eta tear will be equal to W minus N into D into T into sigma T permissible divided by W into T into sigma T permissible. Okay, so this will be the tearing efficiency multiplied by 100%. Okay, this will be the tearing efficiency. Okay, so T and T will get cancelled, this get cancelled, so this will be equal to W minus N into D divided by W, and here N is the total number of holes. Okay, so this is the tearing efficiency for such condition where the width of the plate is known, okay, multiplied by 100%. Okay, so this was the complete information about a riveted connection that may be in a lap connection or a butt connection. Now, the problem, one of the major problem with the riveted connection is they are not leak proof. Okay, so we have to make some arrangements in order to make a leak proof riveted joints, as in previous era the riveted joints were used in boilers. Okay, and in boiler, as we know that boilers have a very high pressure steam. Okay, so for highly pressurized steam the joints should be leak proof. Okay, so there will be some process like caulking and fluorine, so that we will be able to make the joint leakage proof. Okay, so I will be telling you how we can operate that particular method, that is caulking and fluorine. Okay, so previously we discussed about the shear failure, the tearing failure and the crushing failure of the plate. We discussed about the strength of the plate, okay, the efficiency of the plate and the tearing efficiency of plate. Now we have discussed that there will be shearing of the plate. Okay, shearing of the plate, shearing of the plate near the edge. Okay, near the edge. Also there will be crushing of the plate, crushing of the plate near the edge. Okay, near the edge. Okay, now in order to avoid this, we don't have to make any stress calculation, we will be using some empirical relations. Okay, so what is the empirical relation? So as we have seen that if a rivet is placed very close to the edge, if it is very close to the edge, let us say this is the line joining the rivets, this is the row of rivets, there may be n number of rivets in the row. Okay, now as this distance, this is a distance, let us see, this is a distance like this. Okay, now if the distance is very high, then there will be sufficient material to resist the shear of the plate or to resist the crushing of the plate. Okay, now if you don't have a sufficient distance, then the plate will fail under the shearing and the crushing near the edge. Okay, so here we will consider a certain length which should be there in order to avoid this particular failure. Okay, so the distance between the edge, okay, this is the edge and the rivet, to avoid these two kind of failure is known as margin. So let's talk about margin. Okay, margin. So margin is represented by M, and it is provided in order to avoid tearing, okay, sorry, in order to avoid shearing, and crushing of plate near the edge. Okay, so if this is the value of margin, this is the value of margin, then the margin, that is the minimum value of margin, to avoid shear to avoid shear and crushing is equal to 1.5 times of diameter. Okay, so if the joint is there, then D will be equal to DH. Okay, so 1.5 times of diameter is the minimum value of margin. Okay, so you can write that margin may be greater than or equal to 1.5 times of diameter to avoid shear and crushing failure, okay, near the edge. Okay, so this will be the value of margin. Now this margin is used broadly in different types of connection. Okay, now we will see some important facts about the boiler joints. Okay, so we will be using the rivet in the boilers joint. Okay, so according to IBR, that is Indian Boiler Regulation, what is the proper procedure to design a riveted connection for a boiler joint? Okay, so this will be the part of next lecture. Okay, thank you very much.